Good day, this video is to present our digital logic project, which is the Smart Irrigation Control System.
As you can see on the screen, this is our group team. To design our system, we used 3 basic logic gates. On this slide, the AND gate, which requires all inputs to be true. For OR gate, which requires at least one input to be true. And for NOT gate, which reverses the signal. These serve as our circuit's core building blocks. Our goal is to design an automatic irrigation pump controller based on 3 environmental constraints: daytime watering when dry and hot, immediate stopping if wet, and nighttime water conservation. To implement this, we define 4 binary inputs, which is moisture M, temperature T, time D, and manual override O, where a logic 1 represents an active condition, such as sufficient moisture, high temperature, daytime, or an activated override. Based on the situation requirements, automatic watering only activates when it is daytime, high temperature, and dry soil, giving us the expression M bar TD. Combining this with our manual override via an OR gate, we get our final Boolean expression, which is P equals O plus M bar TD. This slide shows our 16-row truth table, which maps out every possible combination to fully verify our simulation results. Now, let us present our simulation results across the 4 required conditions. Condition 1 is, water the field during the day if the soil is dry and temperature is high. On this slide, we set moisture M equals 0, temperature T equals 1, and time D equals 1. The dry signal M equals 0 passes through the NOT gate U9 and becomes a logic 1. Condition 2 requires stopping irrigation when soil moisture is sufficient. We simulated 2 scenarios where the soil is wet, meaning M equals 1. In the first scenario, during a hot day, this high moisture signal passes through the NOT gate U9, turning into a logic 0. This disables the AND gate, driving the circuit output to logic 0. In the second scenario, during a cold night, the output safely remains at logic 0. Both simulation results successfully prove that the pump stays off when the soil has enough water. Condition 3 focuses on nighttime water conservation. We verified this using 2 test cases. In the first scenario on the left, under high temperatures at night, the output from the AND gate U5 is logic 0. Together with the low time signal, the OR gate U2 locks the final output at logic 0. In the second scenario on the right, with dry soil at night, both inputs to the OR gate U2 remain at logic 0, successfully keeping the pump output at 0. Both simulation results perfectly prove that the circuit restricts automatic watering at night. Condition 4 focuses on user control via manual override. We verified this using 2 test cases to prove its highest priority. In the first scenario, we activate the override switch when the soil is already wet. This high override signal goes straight into the OR gate U2, forcing the final output to logic 1. In the second scenario, activating the override at night similarly bypasses the automatic logic, keeping the final output at logic 1. Both results perfectly demonstrate that user control successfully overrides any sensor state at any time. In conclusion, verifying all 4 conditions through our easy EDA simulation proves our circuit design is 100% correct against the truth table. The system functions flawlessly. Thank you for watching.